Section 7.7, transforming exponential and logarithmic functions. Please write down the essential question. How can I transform exponential and log functions? So who uses this? Psychologists can use transformations of exponential functions to describe knowledge retention rates over time. So we are familiar with transformations. We have done transformations on polynomials, quadratics. We never did linear functions. But now we're going to perform transformations on exponential and log functions. It's the same rules. If you're doing a vertical translation up or down, you're either adding or subtracting a k. Horizontal translation means right or left. It's whatever's connected to the x. So x minus h means to the right, h units, x plus h to the left. Vertical stretch or compression deals with this a value out in front. If the absolute value of that a value is greater than 1, it's a stretch. Less than 1, it's a compress. And reflection. Across the x-axis, your y's change, so you have a negative out in front of the function. And if you're reflecting across the y-axis, your x changes, and then you attach a negative to each of the x's. Asymptote is a line that a graphed function approaches as the value of x gets very large or very small. We've dealt with asymptotes already. We've also dealt with the asymptotes on exponential and log functions. So far, we've only dealt with y equals 0 and x equals 0. And now we're going to come across some others in this lesson today. And it's based on the function. So exponential functions always have horizontal asymptotes and log functions always have vertical asymptotes, thus the x equals versus the y equals. Example 1. What we're going to do here is we're given a transform function. We're also given the graph, which we'll work on graphing these in class. And we're going to write the parent function. I'm going to put that in blue. So the parent function of this transform function is 2 to the x. This is the blue graph right there. We've graphed this before in the last half of the chapter, the first half of the chapter. The asymptote, so now what we're talking about is we gave the parent function for this transform function. We're going to talk about the asymptote for the transform function, and the asymptote is y equals 0. And the transformation. So basically, how is it changing from blue to the red? Well, the minus 2 is attached to the x, so we know we're going right or left. And in this case, it's always opposite of what you think, so we're going to the right 2. We graphed them, the red function's the transform function. You can see it shifted to the right 2. We're going to find the y-intercept of the transform function. How do you find a y-intercept? You set x equal to 0 and you solve for y. So I'm going to do that. I set x equal to 0. I have 2 to the 0 minus 2. Well, that's just 2 to the negative 2. Well, we already know what to do when we have a negative exponent. We take the reciprocal to make it positive. And that's just 1/4. So that is the y-intercept. The other thing we could have written as 0.25. So if we look at the red graph, we can see the y-intercept is right there. And yes, that's very close to 1/4. Example 2. Again, the parent function here is going to be 5 to the x. I'm doing something to it. That's the 1/3 in front. And let's write that right now. That would be a compress. And we always write a vertical compress because we don't do horizontal by 1/3. The asymptote here is still going to be y equals 0 right here. The y-intercept, which I'm going to do down here, I'm going to set x equal to 0 and I'm going to solve for y is what I'm trying to write. And again, I'm finding the y-intercept of the transformed function. So if I plug 0 in, I get 1/3, 5 to the 0. Well, that is just going to be anything to the 0 power is 1. So 1/3. That's the y-intercept, is 1/3. And if we look, the red is the transform function, and the y-intercept is right here, and that's close to 1/3. I want to explain these graphs. So the parent function is the blue function. The red function is a transform function. Notice we're not moving it right or left or up or down. We're compressing it. What compression means is we're pushing it towards the x-axis. So the g function, the transform function, is closer to the x-axis than the original. Example 3 we're going to do in class. And now I'm on to logs. So because a log is an exponent, remember we wrote it like this in class, log equals exponent. That's exactly what it is. It's not letting me. I'm going to write it smaller. Transformations of log functions are similar to transformations of exponential functions. You can stretch, reflect, and translate the graph of the parent logarithmic function. And also transformations of natural logs works the same way because the natural log of x means log e of x. So when I look at example 4, I can see, I know that the parent function here, so I'm going to change that. I'm going to call this, I meant to call this G, and this is G. That's the original. So here we go. The parent function is f of x equals ln of x. We're going to find the asymptote. The asymptote of the transform function is right here. It's going to be x equals -1. What are we doing here? Well, we are, number one, reflecting over the x-axis. This is not letting me write very well today. Reflect over x-axis. What else? We're going to the left 1, and we're going down 2. The y-intercept, we're going to set x equal to 0, and we're going to solve for y. So I'm going to do that. G of 0 is -ln of 0 plus 1 minus 2. Then ln of 1 is 0, and so the y-intercept is -2. And you can see that right there. Example 5, we're going to do in class, and there are your video questions.